Okay, calculus. Let's talk about the 9.8 notes, which is power series, intervals of convergence, and radii of convergence. The first 2 pages of the notes are mostly just writing and explanations, but I'll do a quick rundown. So when we were doing the Taylor and Maclaurin series in 9.7, we stopped after a certain number of terms, right? Because we became so accurate. But what if we didn't stop and we just kept finding the derivatives in the next term and the next term over and over and over? Well, what happens there is we create what's called a power series, which is an infinite series that is usually based on some function, but it doesn't always have to be. But it is an infinite series, and if you look at the bottom of page 1, it asks you where they're all centered. Just like for the Taylor series, it's centered at whatever makes the thing raised to the powers 0. So those 3 are centered at 0, -1, and 1 respectively. Now the interesting thing about a power series is power series can usually be written in sigma notation, so a sum, and that means they also converge for certain values of x, which means that kind of represents the viability, the range of viability for what you can or can't plug in based on the center. But this brings together the Taylor series, some of our tests for convergence or divergence, and the series stuff from the very beginning of chapter 9. So this is like bringing it all together. Now, generally speaking, there are only 3 basic options for convergence of a power series. Sometimes it converges only at the center. Sometimes it converges a certain amount out on either side, so it has a radius of convergence. And then sometimes it converges for all values, like the radius is infinite. So those are the possibilities we're left with. So I'm going to start at page 3, number 1, so we can see what the problems look like. It says find the radius of convergence for sum from n equals 0 to infinity n factorial x to the m. Okay, so how do we determine if something converges or diverges? Our most reliable test was the one we learned most recently. And anytime you see a factorial, you almost always want to use the ratio test because it deals with factorials really well. So I really need the limit as n goes to infinity of the n plus 1 term, so that's n plus 1 factorial times x to the n plus 1 divided by the n term, which is n factorial x to the m. This is a very basic problem, but to demonstrate how this works, it's good. Remember that n plus 1 factorial is n plus 1 times n factorial. Also, x to the n plus 1 is x times x to the n. What this allows us to do is to cancel out the n factorials and the x to the n, so I'm left with the limit as n goes to infinity of n plus 1 times x. Now, as n goes to infinity, what's happening? Well, that n plus 1 term is going to infinity. However, it's asking you for what values of x, essentially, and how far out from that value of x I can go. Well, if it's an x to the n, that means we're centered at 0 because there's nothing added or subtracted to our function. But what's interesting is if this is going to infinity, there's only really one value of x that can prevent this from becoming infinite. And that's if x is 0. It's not infinite. Why? Let's just look back at our terms. What happens if it's 0 here? Well, all the terms are 0, and the sum of a bunch of zeros is 0. But that means, though, if I go anywhere away from 0, that n factorial, as n goes to infinity, is going to overpower the x. It doesn't matter if x is like 1/4. Eventually, n factorial is going to be multiplying numbers bigger than 1/4, and you're going to diverge. What that means is there's nowhere out from the center we can go to. So that means the radius of convergence is 0. because there's no space to move around x. Now, how does that compare to, say, number 2? Number 2 says the same thing, but it's now the sum from n equals 0 to infinity of 3 times x minus 2 to the n. Okay, so we could look at the ratio test. We can also look logically. There's no n factorial here. We could use it, but we'll talk more about that in a second. Because if we use the ratio test, the n will disappear entirely. Let's talk about what has to happen here. This kind of has it looks geometric, right? Because we have an a and we have an r to the n. Now what do we know about r? For this to converge, the absolute value of r has to be less than 1. Okay, so what is my r in this case? That means the absolute value of x minus 2 has to be less than 1. So what numbers can I put in there? So that means either if x minus 2 is less than 1 or x minus 2 is greater than negative 1. So x is less than 3 or x is greater than 1. Those are all the numbers between 1 and 3. So where are we centered? We're centered at 2 because it's an x minus 2. So what is my radius? How far out from 2 am I going to get to my 3 or 1? I'm going out 1 on either side. So my radius of convergence is 1. Because I can go 1 out on either side and this thing will still converge. It'll create a geometric series. For example, if I plug in 2.5, which is only a half out from my center, this will be 3 times 1/2 to the n. And we actually have tools for figuring out what that converges to. Let's quickly also do 3. It's the same thing, but it's a slightly more complicated series. N equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Now, when we do this, we get, remember ratio test, we see factorials, takes the absolute value, so it'll be the limit as n goes to infinity of x to the 2n plus 3, remember when I add 1 in there it'll get doubled, over 2n plus 3 factorial, divided by x to the 2n plus 1 over 2n plus 1 factorial, which will turn into multiplication, x to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over, that should be an x, for x to the 2n plus 1. Now if I combine my like terms, how many more x's does the numerator have? 2. So it's x squared. Now just like we pulled out some factorials before, we can pull out factorials here. There are 2 extra factorials though. There's 2n plus 3 and 2n plus 2 in the denominator. Now, what happens as n goes to infinity is this is infinite, the denominator. So it doesn't matter what I do with x, because this is always going to converge. So this always goes to 0, which means it always converges by the ratio test. Unlike the other ones, which have situations, or in the case of the first one, it only goes to 0 if x were 0. So this means the radius of convergence is infinite. And so that's how you find radii of convergence. We'll do more of these notes next.